Hello, everyone. This is Noah Dane, and today's topic for my Geography 408 video project assignment will be our Earth system models and the last glacial maximum. So, first of all, what is the last glacial maximum? The last glacial maximum, or the LGM, occurred approximately 26,000 to 19,000 years ago when continental ice sheets reached their greatest extent during the last glacial period. Massive ice sheets cover most of North America and northern Europe. Atmospheric carbon dioxide concentrations were near 180 parts per million, and global mean temperatures were about 4 to 6 degrees Celsius cooler than pre industrial levels. These dramatically different boundary conditions, including expanded ice sheets, lower greenhouse gas concentrations, reduced sea level, and the increased atmospheric dust, fundamentally alters Earth's radiative balance and large-scale circulation patterns. Because of this, the LGM provides a powerful test case for Earth system models. By simulating this colder climate state, scientists can evaluate how well models represent key feedbacks and large-scale energy redistribution. However, simulations do not perfectly match proxy reconstructions, particularly in the tropical regions, where many models underestimate the magnitude of cooling. In this presentation, the questions I aim to ask are how well do ESMs simulate ice sheet atmospheric feedbacks at the LGM, and why do models underestimate tropical cooling at the LGM? And with that, we first move on to ensemble simulations and ice sheets. With ensemble simulations, the selected simulations are those that best match the empirical data collected. As you can see on the screen, Figure 1 here from Gandy et al.'s 2024 report shows the reconstructed North American ice sheets at the LGM. These models must use accurate ice sheet boundaries as boundary conditions, since these here can impact atmospheric circulation and feedback. Gandy et al. Evaluated which simulations mapped known paleo data. Of the simulations like 4 chosen in the map, some simulations closely match empirical observation, which include its deglaciation ages, margin reconstructions, and flow patterns, like Figure A here, while others do not, like Figure B, too little, and Figure D, too much. Selecting the best simulations is crucial because these ice sheets strongly influence atmospheric circulation and climate feedbacks. And for why the LGM was used to test PMIP models, changes in forcing and temperature between the LGM and pre-industrial are the same order as those projected for the end of the 21st century, making it a great case study for evaluating climate model performance. With the model framework established, we can now examine how ice sheets actually influence atmospheric during the LGM. Ice sheets didn't just sit there. They reshaped atmospheric circulation across the northern hemisphere. Amaya et al.'s study, which happens to be figure 2 on the image, showed that northern hemisphere ice sheets shifted the North Pacific jet stream and altered precipitation across the west coast of North America. The southwest became wetter, while the Pacific Northwest dried, largely due to ice sheet albedo changing ocean temperatures, which reinforced icy feedbacks. As you can see on the left about the zonal wind difference, the winds are faster in the Gulf Stream while slower across Canada due to the ice sheet. And as in figures B and D, you can clearly see that in addition to the Pacific Northwest being drier, you got Atlantic Canada and the area east of Japan as well. The only major western areas are Southwest USA and Baja California. Meanwhile, in arid Central Asia, Chen et al. Found that LGM ice sheets and reduced North Atlantic evaporation weakened westerly moisture transport, producing a cold, dry climate. Later changes in ice volume influenced westerly strength and moisture deliveries. And finally, over Europe, Wisniewicz et al. Reconstructed the Alpine LGM ice cap, and it was revealed that regional circulation patterns influenced by the Fennoscandian ice sheet affected where precipitation fell below across the Alps. In the figure provided for the study, which is the small one here, the blue arrow from the west represents zonal atmospheric circulation dominating from the west near Lyon, while the red arrow here represents meridional circulation from the south, headed at Garda. All three studies in this section reveal that ice sheet topography, albedo, and ocean atmospheric interactions end up driving large-scale hydroclimate shifts in stationary ways, linking ice sheets to changes in temperatures and precipitation patterns far downstream. And with that, we can now talk about model discrepancies. The LGM here provides an out-of-sample test for modern climate models. During the LGM, the total disagreement remains around 2.1 degrees Celsius colder than proxy reconstructions in tropical East Africa, while the mid-Holocene remains 2.3 degrees Celsius warmer than reconstructions. Since proxy system modeling cannot fully resolve the discrepancy, this suggests structural bias in tropical feedback processes. This figure from Marshall et al.'s report shows that most of the changes in the total proxy model, less temperature disagreement, are biased towards worse disagreement for the LGM, while it's closer to better disagreement for the MH. Also, the net difference in the total best case difference is noticeably lower for the LGM, at minus 0.7 degrees Celsius, but 1.9 degrees for the MH. From external model uncertainty, we can now move towards internal model uncertainty within an ensemble. High latitude cooling evidence. In this figure from Becker's report, it was found that the 14 PMIP4 models in this ensemble had highly ranged in the temperature change in the LGM, from minus 3 degrees Celsius for AWIESM2 to minus 20 for CSM21. Of the 14, only 4 of them fall within the compatibility range of minus 8 to minus 10 for Becker's study. Had CM3, ICE, 6GC, INM, CM48, CESM12, and had CEM3, PMIP3. The overestimation of CESM21 lines up with this particular model's previous findings that it likely overestimated the amount of equilibrium warming at Earth's surface, which meant that it wasn't suitable for this ensemble. In addition to ice sheets, aerosols such as atmospheric dust also played an important role in modifying LGM climate feedbacks. Dust and snow played a surprising role in shaping climate during the LGM. Shen et al. In figure 4 here show that increased dust darkening of snow over ice sheets and the Tibetan Plateau enhanced the absorption of sunlight, warming the surface by 2 to 3 degrees Celsius in some regions. This warming would accelerate the melt of snow, alter the radiative budget, and affect atmospheric circulation. Meanwhile, Yang et al. Explained that the snow radiative forcing over the Tibetan Plateau generated anticyclonic anomalies in the mid-upper atmosphere, strengthening regional westerlies and increasing dust emission and transport across East Asia, which served as a positive feedback loop that amplified LGM dust cycles. Finally, Amaya et al., back in the ice sheet slide, found that clouds also interacted with these temperature changes, modifying ocean surface temperatures and reinforcing atmosphere-ocean feedback. As a result, these three studies illustrate how dust, cloud, and ice sheet albedo work together to shape both regional and hemispheric climates during the LGM. Now let's take a closer look at Shen's figure. It's the spatial distribution of annual climate change in the northern hemisphere by snow darkening during LGM. In the change of snow cover rate, most of the snow in the Midwest and around the edge of the ice sheets in northern Russia was lost, while Alaska and China for some reason gained snow. Now, as for the change in the annual average surface temperatures, the report mentions some parts got 2 to 3 Celsius higher, which mainly affects the area by the edges of the ice sheets like Midwestern Ontario and US. And now, as we look at the last one, which is the annual change in precipitation, we can find out that some areas got wetter, like the ocean or the Philippines and Indonesia, while other areas got drier, like this part of Taiwan here and other parts of the ocean. Shaded areas here indicate 95% confidence level, which applies to a small increase of annual precipitation change in North America. Now for the conclusion. In conclusion, when working with ensemble models, it's important to select the simulations with the least uncertainties to get reliable reconstructions of the last glacial maximum. Ice sheets have had a strong impact on atmospheric circulation, forming stationary waves that shifted the jet stream and caused some regions to become wetter or drier. Another key mechanism is the effect of dust on snow. When snow is darkened by dust, its albedo decreases, which then increases surface warming. This warming can then influence monsoon patterns and precipitation distributions. Despite advances in models, Many ensemble simulations still show deviation from paleoclimate observations. These uncertainties need to be clearly explained and addressed, particularly frameworks like PMIP. And finally, in the future, as we look forward, models should incorporate improved parameterizations of cloud and dust feedback, and ice sheet reconstructions should consider stationary weight and be closely matched to empirical data to reduce mismatches and improve climate projections. Thank you for watching my video.